Hey everybody, Dr. A here, and in this video we're going to be exploring another example of two-dimensional rigid body equilibrium. Before we get started though, I want to say thank you for being patient with me. As I'm recording this, I'm suffering from some allergies. I feel fine, I just sound horrible, so thanks for bearing with me as we get through this video together, okay? So let's go ahead and get started. In the given information, we're being asked to draw a free body diagram of the system and solve for the support reactions. So here we have what's called a simply supported beam. Now you might recall that a simply supported beam is a beam with a single segment. One end is supported by an external pin, which is this triangular shape, and the opposite end is supported by a roller, which is this circular shape. Now this beam is 10 feet long, and we have this uniformly distributed load across it of 0.2 KLF, which of course is a kips per linear foot, okay? So let's go ahead and get started. We're gonna start by drawing the free body diagram, partly because the problem told us to, but also anytime you're dealing with a 2D rigid body equilibrium problem, or really any equilibrium problem for that matter, you always need to start by drawing the free body diagram, even if the directions do not explicitly tell you to. So if we draw this free body diagram, we're going to have the beam segment here, and we're going to draw the support reactions. So at an external pin support, we have a vertical reaction and we have a horizontal reaction. So we're going to label those AY and AX. And remember, at a roller support, what do we have? We have a normal force that is going to be normal or perpendicular to the surface the roller is acting on. So this is going to be a BY right here, okay? Now we've got our uniform load. Let me draw that a little bit better for us. Didn't get much better, did it? I'm trying to draw a straight line here. That's better. We've got our uniform load spread out over the length of the beam. That's the 0.2 KLF. And of course, this whole thing is 10 feet long, okay? So this is my free body diagram. Now I'm ready to apply my equilibrium equations. Well, how many equilibrium equations do we have for a 2D rigid body? Well, we've got 3 of them, right? Some of the forces in the x direction equals 0, some of the forces in the y direction equals 0, and some of the moments about a point equals 0. Let's start with some of the moments in the, some of the forces in the x direction equals 0, okay? Not moments, but forces. If we say some of the forces in the x direction equals 0, what we do is we look at this free body diagram and we basically list out all the forces that have an x component. Well, for this particular problem, we only have AX, okay? And so since nothing else has an x component, AX must be equal to 0, okay? There's nothing applied with an x component here. So the reaction in the x direction is 0, okay? That makes sense. Now we can apply the other 2 equilibrium equations to solve for these 2 vertical reactions here, okay? Now remember, do we know exactly what direction AY and BY, and for that matter AX, are pointing? Not really. We know that AY is vertical and we know that BY is vertical, but we don't know if it's pointing up or down. We're kind of assuming that, right? We got to make an assumption, okay? And so we're assuming AY and BY are both pointing up, okay? Now, when we perform some calculations here in a minute, if those values of AY and BY turn out to be positive, it will mean that they are in fact pointing up. If they happen to turn out negative, that means that they are reacting in the opposite of what we assumed, which would be down in this case, okay? So let's see what happens. I'm going to start by saying sum of the moments about some point equals 0. Now, remember, we can sum moments about any point on or off the system. It's typically best to sum moments about a point that will eliminate one of the unknowns from that equation, okay? So in my previous example, I summed moments about point A and I solved for point B, okay? Let's do the opposite now. I'm gonna say, let's sum moments about point B and we'll say counterclockwise is positive. And by summing moments about point B, By will not be in this moment equilibrium equation. What we'll be able to do is solve directly for Ay. So let's do that, okay? Moving left to right, I'm going to say minus Ay times 10 feet, okay? Now, let's pause for a second. Ay times the perpendicular distance to B, okay? That perpendicular distance is 10 feet. Notice Ay is vertical, and your moment arm is the distance that is perpendicular to the line of action of the force, which is Ay. Y negative? Well, I'm saying counterclockwise is positive. If I take Ay and I say, hey, this is causing a rotation around point B, that is a clockwise rotation, and clockwise would be negative here, okay? What next? Does Ax show up here? No. Ax does not show up in this equilibrium equation because Ax lies along the line of action of point B. So Ax does not have a perpendicular distance away from point B. So if you tried to include Ax in there, you would just have Ax times 0, okay? What else is causing a rotation about point B? Well, this uniform load is, right? This uniform load is causing a rotation about point B. So how do I account for that? Well, I'm going to say plus 0.2 KLF times 10 feet times 5 feet. And then I'm going to say all that together equals 0. How did I piece this term together? Well, remember, 0.2 times 10 feet, this part right here, this is the equivalent force. Okay, so think back to equivalent systems. This is an equivalent force that's like right here, okay? What is this distance right here? Well, with a uniform load, that is at a distance half of that 10 feet. So that's at 5 feet away from point B. And so this 5 feet is our perpendicular distance, okay? This 5 feet is this perpendicular distance here, okay? And so I can do a little bit of rearranging, and what will I get? Well, I can just punch this through. This is also kind of these are easy numbers, but 0.2 times 10 times 5 divided by 10, I get 1 kip, and it becomes positive once I do some algebra here because, you know, if I move this term to the other side of the equation, it becomes a positive number. So you know, multiply out, divide by 10, you get 1 kip, and because it's positive, it is pointing upwards, okay? So let's make a note here, make sure we understand this. All right, we're going to say since Ay is positive, it is pointing in the assumed direction from the free body diagram, which is up, okay? Which is up, sorry. Couldn't hear that from my bad voice right now. All right, are we done? Almost. Not quite, but almost. We're going to say sum of the forces in the y direction equals 0. I'm going to say up is positive, okay? So looking back at that free body diagram, we're going to say Ay minus 0.2 KLF times 10 feet. Remember, 0.2 KLF, that is not a force. That is a distributed load. So you have to multiply it by the length over which it's distributed to get a force, okay? And then we're going to say plus By equals 0. Now we know Ay, right? We just solved for it. So that's 1 kip minus 0.2 KLF times 10 feet plus By equals 0. We're going to do some rearranging, and we'll get By is also positive 1 kip, which means it is reacting upwards, okay? So in summary, what do we have here? Say summary, Ax equals 0, Ay is 1 kip pointing up, and By is also 1 kip pointing up. Do these values, 1 kip and 1 kip pointing up, make sense? Well, yeah, I think so. Let's look back at the original figure and the free body diagram, think about it. You have a simply supported beam with a uniform load over the entire length, which means that because of the symmetry, the loading and the geometry are both symmetrical here. That means that AY has to absorb half of this total load, and BY absorbs the other half of this total load. So what is that total load? Well, the total load is 0.2 KLF times 10 feet, right? So this little dashed vector here in orange that I drew earlier, that's 2 kips, right? We saw that here. F equivalent is 2 kips, all right? Can make a note of that here. That's 2 kips. So because it's symmetrical and it's located halfway between A and B, that means that AY has to handle half of that 2 kips, and BY handles or absorbs the other half, hence the 1 kip and 1 kip. So this was a kind of an easy problem because it's kind of intuitive. We know just by looking at this, hopefully, what the reaction should be, but this is how you show your work to get it. And remember, not all problems are going to be this intuitive, so it's important to understand this process and understand how we got these values, okay? So that concludes this example. Thanks for being patient with me with my scratchy, allergy-ridden throat, and please be on the lookout for other content like this. Thanks for watching.